Well, yeah, thank you so much for that introduction. Yeah, this is my first time being here at West Point, so I do want to thank everyone who's been just so gracious and hospitable for the day and a half that I've been here, but it's actually been a really fun time being here on campus. Pamela Harris, I guess I've known since she was a graduate student, so I invited her to come to Purdue to give a talk several years ago, sort of in a similar type of form, and I think that this is where she got the idea from to do something like this. There's actually a lot of people here in the department that I've known for years and years. So Dr. Shoni Johnson I've known for years. Donald Outing I've also known, I guess, since about maybe 2002, 2003 or so. So it turns out that his daughter, Cheryl Outing, and one of your professors, Sam Ivey, were actually students of mine when they were undergraduates. So if you want to get an idea of sort of where you can go in your life, Dr. Ivey here is someone that I knew way, way back when, and now here he is, a professor with his PhD in mathematics. So what I want to talk about today is something that grew out of some research that actually I did with faculty this past summer. This is a program that's called Research Experiences for Undergraduate Faculty. Actually, Dr. Harris was in this program last summer, 2014, right? So here you can see me on the front row. It's really supposed to be a program where we bring in 4 faculty members that lead research for other faculty members. I think that there were roughly 18 or so faculty that were there for the entire week. And the goal is for us to talk about some type of a research project that they can eventually bring back to their own undergraduates at their own institutions. So hopefully a lot of what I'll talk about, it might be a little bit over your heads, but it's supposed to kind of touch on different things that you probably have seen in different classes. So if you don't understand everything, definitely don't worry. The whole idea is just to talk about lots of different topics so you can see how things are related to each other. So here's a specific group of the 5 of us that worked together for that week. Chris Seaton is over here on the left. He's at Rhodes College. Tarina Lewis is new faculty member at Clark Atlanta University. Alfredo Villanueva is at Savannah State. Katie Quartermouse is at James Madison. And just like earlier was announced, I'm over at Purdue in Indiana. So what I'm going to do is try to break up this talk more or less into 3 parts. The first one is just to talk in general about sort of solving polynomial equations. So hopefully you've seen a lot of this throughout high school, but I want to give you more or less kind of the history to motivate some of the words that I had at the title for the talk. I eventually want to get into some motivating questions, and I'll probably get into some things that you haven't seen before, but I still just want to sort of introduce the concepts so that by the end, I'll relate all of this surprisingly to differential equations. So it's really amazing that you can actually go from group theory to differential equations all sort of in the same project. So I want to start with a very simple concept, that is polynomials of degree 2. And it's a very simple question. Given integers a, b, and c, I want to find a number x that satisfies this quadratic equation here, this ax squared plus bx plus c equals 0. Now before I get into the answer of how to do this, I just want to emphasize that this type of equation has been studied by lots and lots of people over the last 2,000 years or so. So really it first got to start with a couple of books by some Greek mathematicians. So this book called Data by Euclid, a very famous book to those of us who did number theory, Arithmetica by Diophantus. There were various Indian mathematicians who also studied this. So some of you may have heard the name Brahmagupta. He's also someone that did a lot of work in algebra and number theory. There were a couple of Persian mathematicians. Al-Khwarizmi, I'll talk about first. If any of you have heard the word algebra, and I'm sure that most of you have, then you'll actually realize that algebra is actually mispronounced. It's actually algebra, because a lot of this came from various ideas that these Persian mathematicians had. In particular, Al-Khwarizmi actually was one of the first people to invent algebra as we know it today. But the story that I want to talk about actually comes down to work of a couple of French mathematicians and a Dutch mathematician. Francois Vieta was really one of the first to sort of look at this whole question here of how do you actually find roots of such an equation. And really the argument that I'm going to give today more or less goes down to René Descartes. But actually it turns out that the formulas that we see in most of our textbooks is due to this Dutch mathematician named Simon Stevin. So just to get to the answers, exactly what we expect. But first I want to say, if you really want to take a look at the interesting history of all of this, I highly recommend this book by Harvard professor Barry Mazur. It's called Imagining Numbers. And really this gets into the history of a complex number. So for example, he actually talks in particular about the square root of minus 15, why that's actually interesting. But if you really think about it, what does it mean to take the square root of a negative number? It actually took hundreds of years to really come up with the right definition of what a complex number is. So if you really want to see what this interesting history is, I highly recommend that you read Barry Mazur's book. But now the answer, of course, comes down to the quadratic formula, right? That's how you find roots of a quadratic equation. So if you have x squared plus bx plus c equals 0, you can find the root x by essentially computing the square. So you have something like this here. This minus b plus or minus square root b squared minus 4ac over 2a. Let me recast the quadratic formula in a slightly bizarre way so that I can generalize the concepts a little bit later. My claim is that the roots of this quadratic polynomial in terms of p of x can be expressed instead in terms of the roots of this function here. So z of w I'll define as w squared, and I actually want to invert that function by taking square roots. And the claim is that if I could take the square root of this number z0, then that's the same as finding the roots of this quadratic equation. Right, so I'll try to go over the proof of this in just a second. But let me introduce some group theory, since I eventually want to explain how this also generalizes. I can permute the roots of this equation by just really taking plus or minus. And the way that I'll do that is by thinking of my square root as being either plus w minus w. So I'm going to define these operations here that just flip the sign of the square root. Right, so I'm writing it again in a fancy way, but it's really nothing surprising. If you take the square root, there'll be two answers, plus or minus. So these will be these operators here. Right, just flip the sign. So where's all of this here coming from? Well, it's not as complicated as you might think. You have your polynomial p of x, and of course you want to try to find the roots x1 and x2. So what we'll do is we'll try to factor this, right? Remember something like the FOIL method. We'll try to factor this quadratic polynomial. And if I stare at the right-hand side, multiply things out, and then look at the coefficients, I then realize that, say, x1 plus x2 satisfies this relation in terms of a, b, and c. x1 times x2 satisfies a similar relation. Right, just multiply out the right-hand side and then compare it with the left-hand side. Let me define this quantity w in terms of the roots x1 and x2. Well, if you stare at this, from the first equation here, I have something involving x1 and x2. From the last equation here, I have something involving x1 and x2. And if I essentially try to work with the top and bottom equations, I can write x1 and x2 in terms of a, b, and w. Right, that's really where that's coming from there. The z0 here is just a matter of realizing that if I define w in this way, then if you square it, right, w squared is exactly the quantity that I had on the previous slide. So notice that the whole idea is that I can express the roots x1 and x2 in terms of this quantity w. So down here, I'll just point out that by permuting the roots, so say for example, if I interchange x1 and x2, then of course that will just flip the sign of w. Right, you can just see that from this here. If you interchange x1 and x2, you'll just flip the sign of w. So again, these operations, w going to minus w, says something about interchanging the roots, something about permuting around the roots. So just kind of keep in mind that I've written this idea of the quadratic formula in a bizarre way, but I want to try to use this a little bit later. So polynomials of degree 2 aren't really all that surprising. We definitely know how to do it. So let's look at polynomials of degree 3. This is where it gets a little bit more complicated. So the question here is very similar. Given now 4 integers, a, b, c, and d, I want to try to find the roots of this degree 3 equation. Again, this is a type of question that's been studied for years and years. Greek mathematicians originally started to look at this about 2,500 years ago. Turns out that Chinese mathematicians also looked at such a question. But really the story comes down to a series of Italian mathematicians who started to look at this type of question. So if any of you have heard of, say, the Fibonacci sequence, well, Fibonacci, the same person, actually looked at such a question here. But But I'm going to focus on these four names here: Scipione da Ferro, Niccolo Tartaglia, Geronimo Cardano, and Joseph Louis Lagrange. So again, these Italian mathematicians more or less tried to look at such an equation, and they realized that by putting together kind of all of the arguments, this is perhaps the simplest way to explain what's happening here. Well, I want to try to find the roots. So this Italian mathematician, Lagrange, actually said, well, let's kind of cheat and sort of write down the answer and then kind of work backwards to make sure that it works. So I don't really want to explain where everything here is coming from because it takes a little while to explain it, but sort of very similar to the way we work things out for the quadratic polynomials, I'm going to assume that my root is sort of like a sum of cube roots. Once you work things out, the cube roots are actually expressed in terms of square roots. And so Cardano and Tartaglia sort of together realized that you can actually express the roots of this degree 3 polynomial only by using square roots and cube roots. Right, so I would say don't really worry about the formulas here too much. It's something you can eventually look up and kind of work out how to do. But the whole philosophy is that you can kind of work everything out here in terms of square roots and cube roots. Well, the history of how all of this came about actually is somewhat interesting. So around 1539 or so, Tartaglia had kind of worked through a series of competitions with mathematicians in the day. Back then, it was really more about you kind of wrote letters to other people, and then you would kind of challenge somebody else to say, okay, here's an equation that I could solve. Can you solve the same equation? But no one really wanted to publish how they solved the equations because, in a sense, they wanted the bragging rights so that they could do it and nobody else could do it. So Tartaglia had worked out kind of the method of how to solve these cubic equations, and his fellow Italian, Cardano, sort of begged him to kind of explain how he could find these solutions. Well, Tartaglia didn't really want to say, but he got a little bit clever one night, and he actually wrote a poem that is the proof. So while I'm telling the story, you can actually read through the poem here and see the poem actually explains sort of what I said on the last slide. Well, as the story goes, Tartaglia kind of asked Cardano, well, just don't tell anybody that I kind of worked this out, but still, here's kind of the proof if you really wanted to see it. Because Tartaglia didn't actually publish anything, there was another Italian mathematician who kind of worked out his own proof, and Cardano saw that it was the same proof that Tartaglia had worked out. So Cardano decided, okay, fine, even though I told Tartaglia that I won't publish his proof, I'll publish this other guy's proof, even though it looks like Tartaglia's proof. So he published it. Tartaglia, of course, got really upset. Kind of some nasty words happened, and essentially there was this really nasty fight between Cardano and Tartaglia about whether Cardano sort of went against his promise of not publishing the proof. But it's kind of an interesting history if you really wanted to study sort of the whole publishing of how to solve these cubic equations. So we sort of give the credit to both Tartaglia and Cardano about solving cubics, but really it was Tartaglia that did it himself. Now, just like I said before, I wanted to try to generalize these concepts of how to actually write down all of these, but remember the philosophy is as follows. I want to find the roots without using radicals. So I'm going to write this in a very bizarre way, and I'll try to explain what I'm doing here. Again, let's come back to this cubic polynomial. I'm going to try my best to actually find the roots of this cubic polynomial. So the claim is I can express all of the roots by doing the following trick. Step 1, let me write down this number here. Whatever it is, I'll just write it down. I'll compute it. Step 2, by some method, invert this function, and then when I evaluate that at the inversion, then I can write down all the roots. Right, so by some method, I'll have to invert it, but this is the idea. Just like before, I can permute around these roots by using these functions here, but don't really worry about this too much. I'll kind of come back to that a little bit later. Okay, so let me kind of skim over why this is the case. So first, let me define these two numbers here, capital A and capital B. and then I'll write down this number here, z0, which is going to be the same number on the other slide, right? Some rational number, I'll just write it down. Just like before, if I factor the cubic polynomial, again, you might remember the FOIL method, I can write it in terms of these roots x1, x2, x3. These are the ones I want to find. And once I have those roots, let me define this w as this ratio of roots here. So if you kind of work through the algebra, play around, now you can express x1, x2, x3 in terms of w. So again, the whole philosophy here is that I can actually find the roots in terms of just this one parameter. Right? I don't have to do a whole lot of work. Notice that there's no radicals here. I just kind of work backwards by saying, once I can actually invert this system here by some method, which I don't know yet, then I can write down all of the roots here. Right, so that's just the main takeaway from this here. If you just wanted to get an idea of, say, how the roots get permuted around, well, this first mapping here that I define, it just interchanges x1 and x2. This one here cyclically permutes, x1 goes to x2, goes to x3. This one here just interchanges x1 and x3. So there's just kind of a way that I can permute around the roots, and I'll sort of write it in terms of these functions here for w. So I'll just emphasize here that this quantity z0, right, this weird thing that I wrote down, I haven't explained at all where it's coming from, satisfies a couple of properties. Number one, a is equal to 0 if and only if z is equal to 0. We can see that from the numerator. B is equal to 0 if and only if z0 is equal to 1. Right, you can see that from the denominator. If b is equal to 0, it's just 4a squared over 4a cubed over 4a cubed. And then finally, x1 equals x2 if and only if w is equal to 0. But if w is equal to 0, stare at this thing here. I get back 1 over 0, so that has to be infinity. So I have repeated roots if and only if z0 is equal to infinity. So somehow this thing, this z0, measures when I'm at 0, 1, or infinity. Right, so that's the thing to kind of keep in mind with the way that I've written down this really weird looking quantity here. So for those of you who feel somewhat comfortable with, say, Galois theory or some information about fields, I'll just quickly say that sort of the high-level approach is as follows. Where all of this is coming from is I'm trying to find the roots of some degree 3 polynomial so I can generate something like an S3 extension. So this here is just going to be, say, some degree 6 extension over Q. Well, the field generated by these 3 roots is the splitting field of that degree 3 polynomial, and I know that there's a theorem that says that every field here has to be principal, so the one element that generates this extension is what I'm calling W. So it's just saying that from a high-level point of view, I know that such a W has to exist. I'm kind of using some deep theorems here. But again, remember that the philosophy is I'm going to take that degree 3 equation in 3 variables, actually 4 variables, A, B, C, and D, and I'm going to change it into a degree 6 equation involving just one parameter. Right, so I'll say that again because that's going to be the whole emphasis for the rest of the talk. I'm taking this weird looking polynomial in 4 variables, this A, B, C, D, and I'm going to rewrite it in terms of just one degree 6 equation in terms of just this one parameter z0. So once I can find the solutions to that one, for that one parameter, then I'm done. Okay, so now that we've done degree 3, let's just try to see how bad is it going to be if we try to do degree 4. Okay, same basic idea as before. Given integers a, b, c, d, and e, we'll try to find roots of this degree 4 polynomial. So again, this has been studied by a lot of people. It turns out that the same people who kind of worked before, so people like Tartaglia, Cardano, they also worked in the same type of problem, and I'll explain why in just a minute why they really did this. But a lot of what I'm going to explain actually comes from Vieta and Lagrange. The formulas are actually pretty nasty, so I'm just only going to skim over it. But just to say, if you wanted to look this up in a textbook, it's really bad. Programs like MATLAB and Mathematica, essentially they just memorize the formulas and just spit this back out at you because of how bad they are. So just to kind of skim over the ideas, I take my P of x, I then factor it in terms of these 4 roots. I then do a clever substitution. Again, I'm not explaining where it's coming from, it just works. Where I write x1 through x4 in terms of square roots of some other root. Well, that other root, it turns out, has to be the roots of a degree 3 polynomial, where these are the coefficients. So here's the idea. I take my degree 4, I reduce it to a degree 3. I know how to solve a degree 3, I just showed you how to do that. So I use that to then work backwards to then solve the degree 4. Right, that's really the whole philosophy in a nutshell when you're trying to solve a degree 4 polynomial equation. So Ferrari essentially just says this. I can write the roots of any quartic in terms of square roots and cube roots. Right, so I can just use radicals to find the roots of a degree 2, degree 3, degree 4. I only need it where square roots and cube roots to do these types of polynomials. So just like before, let me try to motivate sort of the idea of how we should be able to do this kind of using or not using radicals at all. I'm going to make the small assumption here, but don't really worry about it. It's only just to make the formulas on the slide here look a little bit cleaner, that's all. Well, I can write the roots of any degree 4 in terms of the inverse for this function here, where the one parameter I use is this z0 here. So without really going over what all of this means here, I'll just simply say that when I permute around the 4 roots, I get back the symmetric group in 4 elements. I mean, it kind of makes sense. So how do you permute around 4 elements, right? So I get back something like this. But again, this is the whole idea. I can write everything in terms of this one function, this one parameter. So I'll just kind of skim over where this comes from. It really is pretty bad to explain. I can write my a and b in this way here. I then expand out just kind of by multiplying out the polynomial. This is my w. Again, don't really worry about so much where it comes from. It's not extremely important. But then you get these horrendous formulas here. But the main thing to take away here is I'm not using radicals. Once I find the one root here, just one w, here are all of the roots. Again, just to kind of hit home where this z0 might be coming from, a is equal to 0 if and only if z0 is 0. B is 0 if and only if z0 is 1. And I have repeated roots if and only if z0 is infinity. So intuitively, I'm going to try to stay away from 0, 1, infinity. That's sort of the idea. And just like before, if you want to think of this from kind of a high-level point of view, I have my degree 4 polynomial. I have an associated degree 3 polynomial. So I then have something like an S3 extension, which then should correspond to an S4 extension. But by the primitive element theorem, I should find one element that kind of generates that extension. That one element is what I'm calling this W here. But the main thing to take away from this whole slide is the following statement. Given any degree 4 polynomial, I can write down one parameter, z0, so that the roots of this degree 24 polynomial, 24 is 4 factorial, once I have one root here, then I can write down everything else. So again, I'm not using radicals, just saying once I have just the one root here, I know everything I need to know. So of course, at this point, a couple of questions should start to come to mind. One, where are all of these formulas coming from? And two, why are we just doing it case by case? Can't we just do this like in a general way and work it out that way? So let's try to focus on those two questions. And one is, okay, let's try to do polynomials of degree 5. So we've done 2, 3, 4, what about 5? Again, the question is, I have here A, B, C, D, E, and F. I'm going to try to find the roots of this degree 5 polynomial. Various people have worked on this. And over the years, people have realized there's a problem. You can't write the roots of a degree 5 in general in terms of radicals. So I can't do something like square roots, cube roots, maybe fifth roots. I definitely run into a problem. I'll just throw this out there because I won't have time to really go into any detail. A lot of people know about Edray Goins, that he actually died at the age of 20 after a duel. And so a lot of people really think that this is fascinating, that he was only 20 years old and he actually proved a theorem like this here. Well, what a lot of people don't know is that really before he really worked this out, Niels Abel died at the age of 27 and really had a much more powerful result. So it turns out, if any of you have heard of something called the Fields Medal, this is sort of like the Nobel Prize for Mathematics. Really, currently, the Nobel Prize for Mathematics is actually called the Abel Prize because it is named after Niels Henrik Abel. Okay, so again, we're stuck on degree 5, but let me just kind of recap what we've done so far so I can then explain where we might want to go next. So here, if we have, say, a degree 2, if I write down this function, z of w is w squared, here's my parameter z0, I invert it, I have all the roots. If I have a degree 3, here's my parameter z0, I set this equal to z0, invert it, I have all the roots. If I have something of degree 4, here's my parameter z0, I can invert it, I can find all the roots. And of course, we know we can't do degree 5, or at least we know that we can't do it in terms of radicals, so we have to be a little bit careful to figure out where to go from here. Right? But the point is that if I can somehow do something like this, then maybe I can sort of work things out without using radicals. And yeah, Pam, how am I doing on time? Okay. Okay, so these are the two motivating questions that I wanted to give my group over the summer so we can kind of figure out sort of where we're going, right? What's the step here? Say that you give me a polynomial of degree n. So we've already done degree 2, 3, 4. Say even if you give me something of degree 7, right? Just any nasty polynomial you can think of. Can I do this trick all over again? Right, so say I find a polynomial, a rational function, say of degree n factorial, that just depends on this coefficient z0, just the one parameter, so that somehow the roots of that polynomial corresponding to kind of inverting this z of w equals z0. Right, so I want to know, can I just reduce everything down to just one parameter and then do this? Well, the second question then says, okay, fine, how do I actually invert such a function if I could do this? So these are the two questions I want to focus on next. How do I find such a parameter? And then how do I actually invert it once I can do this here? So the way that we're going to do this is actually going over a little bit more history that goes in a slightly different direction. And this kind of gets into the title here of monodromy. So it turns out that there was a German mathematician by the name of Felix Klein that essentially said, all right, I've looked at, say, polynomials of degree 3. That's what I'm calling here S3, symmetric group on 3 elements. I know what's happening for degree 4. That's the symmetric group on 4 elements. So what I can do is I can kind of write down these groups in a very clever way. Right? If you've never seen groups before, don't worry about it. The idea is that I can permute around the roots of a polynomial and do it in such a way that I can kind of write down these cute little formulas. But the main philosophy is that there's only a finite list here. Right? So in particular, I just want to point out that there's really only these 4. But again, Klein worked this out in about 1890 or so, just saying, okay, well, I can kind of do this in a very nice, clever way. The important statement is, once you have those groups, you then have kind of the right rational functions. So this is something he worked out about 130 years ago, saying that, well, here's the idea. For each one of those, in particular, I only am going to focus on these last 4. These are the right types of functions to work with. So there's something deeper happening here that I'm not really explaining, but the idea is that he definitely knew that these 4 are the ones to work with. This one here should look familiar. This is what we did for the degree 3. And this one here should look familiar. That's what we did for degree 4. Right, so that's really where those functions are coming from. It's sort of this idea of Klein that these are really the right ones. It's hard to explain where these are coming from. Part of the reason is he wrote everything in German. And for example, when I was in graduate school, my advisor handed me Klein's book and said, okay, I want you to read this and understand it. The book was in German. I don't speak any German. So it took me a long time to kind of figure out what all of this stuff here meant. Right, so it's really not easy to explain, but still, it can be understood. Okay, so remember, this is the idea of what we're trying to do here. I have one of these groups. I have one of these maps. I just showed you in the previous slide. And let's say that I have a polynomial that kind of corresponds to one of those groups, like S3, S4, what have you. I want to know what's the right coefficient z0, remember just the one parameter, where I can write all of the roots in terms of that parameter. Well, we know how to do this for degree 3. We know how to do this for degree 4. The question is, how do we do this for degree 5? Well, I can tell you for the group that we work with over the summer, we're still sort of working on this. So unfortunately, I can't really give you an answer here. More or less, Klein worked out the answer, but he did it in such a weird way that it's hard to really explain. But the point is that, yes, there is a way you can actually answer this question, but still for our group, we're still trying to work on how to actually get this to work out cleanly. But again, remember that the philosophy is for each one of those groups I wrote down before, there should be kind of the right thing here. The z of w, I just showed you on the previous slide what those were, but the right thing is this. Let me just say this here, since I know a lot of you have not seen this group A5, this corresponds to polynomials of degree 5. So this last case here, I'm going to use to explain how to write the roots of a degree 5 polynomial. Okay. So the last thing to kind of put all of this together is this question here. I showed you all of those functions that Klein had worked out. The last thing I want to do is explain how do I invert these. Essentially, if I can invert them, then I can actually use the invert to find all the roots. So from here on out, I'm just going to do differential equations. Okay, let me start with a very simple question. Let's consider this function here. So something like z of w equals w squared. Right, so just a very simple function. I'm going to associate a differential equation to this function here. Well, the simple way that we'll do this is take this function, take the log of both sides, right? If z is w to the n, the log z is n log w. Now just take implicit differentiation, and I get something like this here. Right, so again, just take the derivative, implicit differentiation, it just all kind of works. You'll notice that when z is equal to 0, I get back a problem. So this is what's called a singularity for the differential equation. It turns out when I take z goes to infinity, it's also a singularity. I'm not really going to worry about why for the sake of time, but I'll simply say that there's two poles for this equation, 0 and infinity. This is actually part of a larger statement that says that if I have any first order equation that has exactly two poles, it basically has to be in the form that I had before, right? That's the statement here. So this z to the w, namely this thing here, is kind of uniquely determined by the differential equation. Right, that's really the surprising thing here. So inverting this thing here, again, the inverse of this function satisfies a differential equation. So I'm going to use this for these other functions I'm writing down. All right, let me just ignore this for the sake of time. Let's take a look at what's called a hypergeometric differential equation. So it's just written in a very specific form. So here a, b, and c are just complex numbers. I'm going to define this lambda, mu, and nu, so just three other complex numbers from these given a, b, and c. And essentially the statement is, number one, this equation is uniquely determined that it has exactly three poles, 0, 1, infinity. Right, remember the 0, 1, infinity that I mentioned at the very start. Number two, I can actually write down the solution. If any of you played around with power series, you just write down a power series. Right, that's all that it is. So the point is that I can actually write down the solution here. It's very simple. It's really nothing complicated. You can do this as a homework problem pretty easily. So if you want to see an example of how this works, well, if I had this power function like before, the inverse is a root of some hypergeometric equation where I can choose lambda, mu, and nu in this way. This other weird function here also satisfies the hypergeometric equation where lambda, mu, and nu are these numbers here. So I was playing around, just looking on Wikipedia a few years ago, and I came across this weird page. They called it here Schwarz's list. And let me just zoom in so you can see this. And I noticed that it just had these weird numbers. It still had lambda, mu, and nu, but it had these weird looking numbers here. So I really stared at this for a couple of hours, and I really couldn't figure out where any of these numbers here were coming from. So I figured, if I'm going to stare at it for a few hours and not get anywhere, why don't I have other faculty stare at it for a few hours and not get anywhere? So this is what I gave my other faculty members for the summer. I basically said, look, you have these numbers, where are all of these coming from? Now, here's the simple way to explain where these are coming from. It's actually embarrassingly simple. So let me ignore this. Let's come back to this differential equation. My claim is, if I know two solutions to this equation, remember on the last slide I showed you what two solutions were. You can write them down. Take a look at this ratio. Then once I define what's called the Schwarzian derivative, then I get back this over here on the right-hand side in terms of lambda, mu, and nu. So in particular, if I take those functions that Klein had, here's lambda, mu, and nu. That was exactly what was in Schwarz's list. Just take Klein's formulas, multiply it out, it all works. So the last slide is this one here. If I have this ratio, then I can take any one of these maps from Klein's list, and essentially I can invert them. So unfortunately, I'm not going to have time to really go into any more detail about this, but again, the idea is that, say here, if I have degree 3, I set this equal to some w, some z0, but the inverse is this here as a function of z. So if I want to find the roots, I just plug in z0 here. Remember that it's kind of a work in progress for us to do all the other ones, so we only kind of did just a few of these here, but we're still trying to work to kind of get the rest of them done. Right? But again, the whole philosophy here is that we didn't need any radicals at all. We're just using these so-called functions to kind of work it out. Right? Okay, so I know time is short, so yeah, so thank you for your time and attention then.